Today we're going to start look at the triple integrals, which you saw in the videos before today. What we're going to do, I'm not going to spend a ton of time talking about the theory. I'll mention a couple things. I'm going to spend more time today showing you how to leverage CalcPlot 3D to set them up. And then we'll spend some time afterwards on some worksheet problems, calculating a couple, and yeah, that was great. You guys are simultaneous. Pull out the laptops, because yeah, you especially in the early going, you're going to want to kind of get an idea of what these 3D things look like. As you get better at these, there are going to be ones where you don't need CalcPlot 3D, but obviously some of the more complex ones, just like with the 2D integrals, we need to think about the order of integration. What's going to make sense? What's going to work? So that's what we're going to spend more time on. So let's dive in. So now with the double integrals, we were integrating a function of two variables over a region in the XY plane. Now we're going to be able to integrate a function of three variables over a 3D space. Okay, so if our function of three variables represented density, we would be getting the total mass of the object. And so basically we do the Riemann sum. So the same thing you did all the way back in Calc 1, where you broke it up into rectangles. Last time, you know, we talked about breaking it up into rectangles in the 2D plane, and those had columns on top of them. Now we break up the region into some three-dimensional blocks. Okay, and those get at the contribution of each block gets added up to estimate the triple integral. We eventually take the limit as the lengths of the sides of the block go to 0, which makes it the actual triple integral and exact. So we get what is a triple Riemann sum. All right, that's not that important for us. We're not going to be doing these as Riemann sums. I just like to relate it to what you were doing in Calc 1, what we did with the double integrals. All we're doing is adding on another layer. All right, and so we get a triple integral. Just like with the double integrals, it's really nice if all our limits are constants, because then the order doesn't matter, at least as far as the limits go. Like one order might be easier for integration than another, but if all of our limits are constants, it becomes very easy. And now kind of adding to what makes these a little bit trickier, because there's three levels, there's 6 possible orders we could go in: dx, dy, dz, dx, dz, dy, right? So on and so forth. I'm not going to go through all of them, but we have to be careful. You know, we want to be very intentional about how we choose our order, and that's what we're going to basically look at. So I'm actually not going to do this one. We might look at it later if there's time. This one is actually the easy case, because our region is just a rectangular box with corners at 0, 0, 0, A, 0, 0, 0, 0, B, 0, 0, C. So our limits are 0 to A, 0 to B, 0 to C. And the order really doesn't matter. We can put those in any order we want. Okay. As far as doing the integration, it's the same thing you were doing with double integrals. It's just now you have to be even more careful, because now you're going to be integrating a third time. And your inside limit can now be a function of 2 variables. Can be, it doesn't have to be, instead of just 1. So let's talk about this first, because this is something we need to be able to do. We have to be able to go in both directions. We have to be able to take a region and set up the limits, but we also have to be able to take the limits and set up a region. All right. So we need to know what this region here looks like. So look at what's happening. Y is going to go from 0 to square root of 1 minus z squared. What that tells me is that in my YZ plane, this thing, so there's our Y, there's our Z. And I know this is Y equals, because dy, so Y equals, so first thing we have to plot is Y equals square root of 1 minus z squared. Like I said, I mentioned this when we were looking at double integrals. You've got to get used to seeing these forms. Like we need to know right away that this is a half a circle. Because if I were to square both sides and add the z squared over, I'd have y squared plus z squared equals 1. Now it's a semicircle because of the square root. I can't get any negative y values. So I get a half a circle in the YZ plane with a radius of 1. You will get really good at recognizing these regions. Okay, now we go to the next set of limits. Z is going to go from -1 to 1. So it is the whole half circle. If Z was going from 0 to 1, it would just be the top quarter. Obviously, Z could go from like -0.5 to 1, something like that as well. And we can handle it because we know what that inside shape looks like. All right, so right now we've handled the first two sets of limits. That's what it looks like in the YZ plane. It's a half circle. Z is going from -1 to 1. X goes from 0 to 1. So let's put in our x-axis coming, imagine that coming straight out of the board, right? So there's our x. And all x does is go from 0 to 1. There's nothing else changing that circular shape. So what's going to happen is we're going to get basically, it's hard to, I'm not the best at drawing in 3D, but we're going to get half of a wheel, basically. And there's our x equals 1. So what we got is a half circle with a little bit of thickness to it. So that's our region. Questions about that one?
It's just a little hard to like picture the 3D-ness of it.
Yeah, my drawing's not great. I'm not going to draw a whole bunch of these regions, but I mean, this one, but we need to have an idea on some of these. And all my drawing has to be is good enough for me to say, okay, this is what this region looks like. Doesn't have to be perfect, but we need to be able to draw some of the basic regions because we have to figure out what order of integration makes sense. This one, the order is already set for us because we're actually drawing a region.
Is this something that can be asked on the exam? Like if we're given
Could be.
okay.
Yeah. Yeah, and as far as the exam go, the regions will be reasonable. They'll be very common, circular, spherical, things of that nature. The ones we're going to look at today are probably going to be a little more complicated than what I would give on an exam. Because we do have Calculate 3D available. Maybe not the first one, but a couple of the other examples, I would want you to have Calculate 3D available to set your regions up. Those would be more like take-home problem level. Okay. So one thing we need to be able to do is draw the region given the limits. Now, from a practical standpoint, we're not going to do that a lot. What that does, though, is help us to visualize what's going on, the relationship between the region and the limits. Because more often than not, we're going to be going from the region to the limits, which is what we'll do in this next example. All right. So we're integrating over whatever function. So again, today, most of my time is going to be spent on setting these up. We've spent time doing integration. Now you just have to do it 3 times instead of just 2. So I think you're going to pick that part up really quick. It's the limits that we need to set up. Now it's kind of hard to see the region from there. So there's the 3D image of the region. Okay, so that's our region W. We're talking about some triple integral over W of f of x comma y comma z and dv. Some order. We'll decide the order later once we figured out our region. Okay, so Maybe we'll look at a couple different orderings on this one, because that's going to be one of the things. Remember, they're all constants. There's 6 possible. So we're going to have a lot of situations where more than one is possible, but one might be better off for us, or one might be easier. And we'll do that when we go through the examples. I'll show you on ones that can be done 2 ways very easily. We'll do that. On ones that can't, we'll talk about why. All right, so let's talk about our limits. So notice that this thing is spherical, right? Remember that sphere x squared plus y squared plus z squared equals radius of 4. So equals 16. That would be the sphere of radius 16. Now I'm just putting that up there as kind of a jumping off point. But we're going to need to manipulate this to decide what order we want to do this in. This one's going to be one we can do in any order. So let's just say we decide to start with z. All right, so notice that z, there's no negative z values, right? And it goes up to the sphere. So that sphere is our upper bound. So we're going to want to solve this for z. So the square root of 16 minus x squared minus y squared. So let's give ourselves some room here. So 0 to square root of 16 minus x squared minus y squared. Some function, whatever it is. We would deal with that later. And we decided to do z first. This is what we were talking about before. Now it becomes a double integral. All right. Z is no longer a factor. So what you want to look at is what I call the shadow region in the XY plane. Because here's the thing. We need to cover all the possible X and Y values. See, that's why I call it the shadow region. If you were to point a light directly down whichever axis you do first, whatever you see in the XY plane, that shadow is your region. Now on this one, our shadow being cast is that semicircle, right? So if we want, we can basically draw a plot of that in the XY plane. And if we look at what's going on, we got the half circle. We have no negative y values, right? So it's doing this. And it's a half sphere of radius 4, right? Or not a half sphere, half circle of radius 4, which y in terms of x, that would be y equals square root of 16 minus x squared. Now, and this is not coincidental because we're all working off of the same sphere. When we're down in the XY plane, z has a value of 0, right? Well, I could have gotten this equation by finding the trace of this when z equals 0. That would leave me with x squared plus y squared equals 16, solve it for y. All right, like I said, you are going to see so many circular regions between now and Thursday that this formula is going to become second nature, and you're going to recognize it as circular or spherical. But while you're getting used to it, I just want to show you the relationships. And so y clearly is going from 0 up to the curve. So 0, the square root of 16 minus x squared. That takes care of dy. X, not so bad, right? Goes from the negative radius over to the positive. Radius is 4, so it goes from negative 4 to 4. So negative 4 to 4, and there's our dx. Okay. Questions about that setup? All right, let me show you an equivalent one. Maybe I decide to do x first. All right, so if I look, I'm going in the x direction. Now we do get negatives. And it's going to go from the negative side of the sphere to the positive. So now instead of solving the sphere for z, I'm going to solve it for x. And it's got to go from the negative to the positive. So negative square root of 16 minus z squared minus y squared to positive 16 minus z squared minus y squared. Got our function in here. And now we're doing x first. Okay, so now it flattens into the YZ plane. Doesn't matter which one you put on top, it's kind of up to you. Why maybe Z is there, Y is here. Well, I've got my YZ plane right here. It's the quarter circle. Still has a radius of 4. So the equation on that guy is going to be Z equals square root of 16 minus Y squared. And I just realized I wrote right into our problem. So let's actually move this guy. So all we got is that quarter circle in the ZY plane. So Z equals square root of 16 minus Y squared. And there's no negative Z values. So if we want to do Z next, we're fine. Square root of 16 minus, oops, I'm missing a square there. Excuse me, Y squared. That takes care of our dy. And Y is going to go from 0 to 4. This is one we could have done any order. So there's 6 possibilities. And obviously, I don't think it's worth our time to go through them all. But I just want you to start to get the idea of, okay, if you can get that first set of limits, after that, it's a 2D problem and it becomes much easier because we can draw it. We'll talk a little more in the shadow region about the shadow region in another problem. Okay, questions about this one? All right. Unfortunately, I don't have much board to work with, so every time we come up with a new example, I got to erase the old one. But here's going to be the next one. Take a look at that while I get the board erased. Now, if you remember with double integrals, we said, hey, if we let the function be 1, then the double integral finds the area of the region. With triple integrals, if we let the function be 1, it gives the volume of the region. So from here, for the next few examples, I'm just going to let the function be 1, so I don't have to deal with it, because I want the focus to be on the limits. We can always put a function in later and integrate over it. It's the limits that need the work. Once we know the function and the limits, Symbolab or Wolfram Alpha can finish off the problem. What it can't do is find our limits. So we need to see what this looks like. Give me just a second. And there. All right. I already put in the, come on. It should work. It worked earlier. This just worked. Oh, there, let's try that. All right, give me just a sec, getting it up on in the classroom as well. And there we go. So here's our region. I already put the functions in, so I'm going to go through those with you. I went ahead and put the y equals 0 in there. Oh, sorry, that's not the one. This is the one I want to look at first. Okay. So there's a few things I want to show you. So I put in the functions over here, right? Y equals 0, x equals 0, z equals 10, and z equals x plus y. So this is going to be a really good example to talk about the shadow region. This is what our 3D object looks like. And we can see that it creates an enclosed volume right here, right? Everybody see that okay? Now, when you guys go to do these, remember, if you're not sure which which surface corresponds to which function? Turn them on and off. Okay, so there's x equals 0. It's the blue one, right? So you can always find ways of checking them. So there's our 3D surface. Sorry, not surface, 3D object. And we're going to find the volume of this thing with a definite integral. We talked a lot, if you remember, I talked a lot in double integrals about having a definite left and a right, or a definite top and bottom. Same thing essentially goes with triple integrals. The thing that's going to make these easiest is if you can identify a top and a bottom, or a clear left and right. Now, this is going to be one that can be done a multitude of ways, but there's one way that I think is easier or more obvious than others. And so what I notice on this one is if we look at the way the limits were given, we were given z equals x plus y and z equals 10, right? Well, z equals x plus y is the only slanted plane in here. It's this blue one. And z equals 10 is this yellow plane. And if we're not sure, turn it off, turn it on. There you go. Well, notice how this makes the bottom of our region, right? And the yellow makes the top of our region. That makes those excellent candidates for the inside limits. So as we go to write this thing, our inside limits are going to go from x plus y, because that was on bottom of our region, up to 10. And that's doing z first. Again, we're assuming the function is 1, so it doesn't need to be written. If we had a function that we wanted to integrate over, we just plug it in. I can't stress how important it is that to get those first two regions. Everything else is a 2D problem. So if you have questions about that, let me know. But here's what happens next. This is the perfect example to start to talk about the shadow region. Because if we look at our 3D image, there's no region in the XY plane. But if I were to look directly down this thing, let's see what X. I want to do one thing. I want that X to come up a little bit higher. Why is it not? There we go. So you can see it a little more clearly. There we go. All right. See how I've got this region here if I were to look directly down this thing? So there's my positive X, there's my positive Y. That is where the plane hits. That's the shadow region. Again, if you were looking directly down this thing, what would it look like in the XY plane? Where does that come from? Well, it's basically the intersection of these two guys. So it's basically the intersection of where z equals 10 and where z equals x plus y. So in the 2D plane, it's where z equals 10, so put the 10 here. It's where 10 equals x plus y. That's the region in the XY plane. That's what's making that triangle there. So now we have something we can graph. X plus y equals 10. Well, that means we've got intercepts of both positive 10 and 10. We know we don't have to go over to the zeros. There is our region in the XY plane. Again, now we're back into a double integral. This is stuff you already have plenty of practice on. And we know, hey, there's an obvious left and right if I want to go X first, and there's an obvious bottom and top if I want to go Y first. So the equation for that line, y equals 10 minus x is one option. So we'll do y next. And y is going to go from 0 up to 10 minus x. And then x is just going to go from 0 to 10. Okay. Questions about any of those limits? Okay, let's do this one in do it in a different order. Not that that's gonna, well, there might be one or two that you might be asked to change the order, but Now that, most of the ones we're gonna be doing, we just want to be setting them up, but I just want you to realize that there's more than one ways to set these guys up in a lot of cases. So let's get this out of here. All right. So we did it with a top and a bottom, but I could have done it with like a left and a right, because notice that this plane, this blue, the darker blue, not the light blue, this darker blue plane could be one of our boundaries. So I could be going, let's say we wanted to do X first. Well, we know X goes from 0, which is this blue plane. I know they're both blue, but light blue plane out to the dark blue plane. Okay. So how do we do that? Well, again, the first set of limits usually aren't too bad. So first thing we're going to do is so this time we're going to do dx first. I forgot the other, we did, sorry, dy dx. Alternative. So we're going to do x first. X is clearly going from 0 out to the plane, which was given as z equals x plus y, except now we want it as a x limit, right? So we're going to solve that for x. So x equals z minus y. So that's our upper. Okay, and we're doing x first. Everybody okay with that? Here's why this is nice. We are now back to a 2D problem. So what have we done? We've already integrated with respect to x. So now here's our region in the xz plane. Excuse me, the yz plane. There's our region in the yz plane, another triangle. This is the positive y-axis, it's backwards just because I want you to see it, but it's another triangle. It's going to have a top at z equals 10. This is the z-axis. There's your y-axis, and this is that slanted plane. Okay. So let's talk about what these look like. So now, and this is again where you can use Calcplot 3D in order to draw these things. Okay, so what's happening? Well, I know it's getting cut off here because y equals 0 was one of our planes. We got this slanted plane coming through like this, and it basically is at a 45-degree angle. Remember that now we're in the yz plane, so we're where x equals 0. So if we take these two things together, that z equals x plus y, that's the plane in 3D, and we're in the plane where x equals 0, that's the trace we're looking at. That's going to go in there, and basically that line is z equals y. And then we know it's capped on top by z equals 10. Right, that plane that came right there, that's the plane z equals 10. This is our region. Again, back to a 2D problem. I can't stress that part enough. That's what I want you to feel like. I want you to feel like, okay, the inside limits are something new, but this second and third set of limits are stuff we've been doing. So we can go in either order. I got it as z equals y. It's real easy to flip over to y equals z. It's kind of up to you. Let's say we decide to do dz next. Now the bottom is z equals y because we want above it, right? So our lower limit is y, our upper limit is 10. And now we can see that y is going to come from out here, and it needs to get to this point right here, which is where z equals y, so that's basically the point 10, 10. So y is going to go from 0 to 10. Questions about either of the orders on this one? So again, you might do it different than the person sitting right next to you. Don't let that bother you because there's different ways to do them. What we need to be is consistent. What we need to do is look for that definite top and bottom, definite left and right. Where are we starting and where are we ending? Okay. And I'll show you one in a little bit where we need to be a little bit more careful, and there's more of an optimal way of doing it. Okay, questions about this one? All right, then next one. Let's add in a little bit more. So that's gonna be that guy there. Here is that region. See if you can kind of start to identify what plane, and now here's your positive Z, your positive Y, and your positive X is right here. See if you can kind of start to identify which equation corresponds to which piece. This one's a little tricky. There's a little bit more going on. I'm gonna have to erase the board. And this is being recorded, so don't worry if you didn't get all these notes down. You can always go back through the video on these examples as well. Okay, so this one to me has some similarity to the last one in that when I first look at it, I kind of see a definite top and bottom in Z, because clearly this yellow plane is making a floor on Z, and that corresponds to the plane Z equals -6. And then I see this kind of greenish plane here. Let's see if we can do a color that's maybe a little. Let's do this. There we go. That makes it a little more distinct, right? Notice what the plane that corresponds to. This one right here. But notice it does make the top of our region. So this is a great candidate for inside limits to go from -6 to this pink plane. That means I'm going to have to solve that one equation for Z for my upper limit. So my inside limits, -6 to 4 minus 2x minus y. Again, we're just doing volume. Any function can be put in there at any time, okay? Biggest thing on triple integrals is getting in the limits. The second thing is obviously if you're doing one by hand, there's a lot of places to make a math error. You're doing a triple integral. But as we've talked before, that's where you can leverage Wolfram or Symbolab. Make sure you have it set up right before you go cranking it out by hand. So that way you can focus on the setup. Once you know the setup's right, then you can practice doing some of them by hand. All right, got our first two limits. This thing just got a lot easier. So now we got to think about our shadow region. Now the shadow region needs to be where the X and Y are the biggest, which is down here in the plane Z equals -6. So that's making this triangular shape right here. We got to be a little careful about what that looks like. Let me see if I can, let's make that plane a little more transparent. See if that helps. No, I don't do that. And okay, let's keep it this way, but up the transparency. All right, because notice in this case, all right, we got two slanted lines, and then we've got this guy here, which corresponds to y equals 0, right? So this is what it's going to look like in the XY plane, except it is backwards. My positive X is over this way, right? So it's because I'm looking at it from bottom up instead of top down. But I wanted you to really see the shape. Okay, so we can start to draw this thing, and then let's talk about what kind of things we got going on in here. All right, so it looks something like this. Okay, that's kind of a rough sketch of our region. Again, this is the positive x-axis, so this is kind of a mirror image of it. All right, let's talk about where those lines come from, which one is which. Now remember, we're in the plane Z. This is happening in the plane Z equals -6. So one of our equations is coming from y minus x equals 4. And one of our equations is coming from the combination of this guy, 2x plus y, plus z equals 4, and z equals -6. So that -6 will plug in here, right? Because that's the plane we're in. Add it to the other side, and this becomes 2x plus y equals 10. Make sense? Now, a couple different ways we can figure out which equation corresponds to which part on our graph. One way is to use Calcplot 3D, right? Turn off y minus x equals 4 and see which one turns on. We don't need that though, because here's the thing. If I solve each of these for y, this would be y equals -2x plus 10. This one here would be y equals x plus 4. No, oh, sorry, I should put the axes on here so we can. Well, that one has the positive slope. So this is y equals x plus 4. This one has the negative slope. So this is y equals -2x plus 10. Okay, and obviously bound below by y equals 0. Now, right now, I have it set up to do y next. Well, that's great, but if we're doing y next, notice the bottom and top is different here than it is here. So that would mean if I decide to do y next, I need to split this into 2 triple integrals. It wouldn't change the inside limits, but I would need one triple integral going from 0 to x plus 4, and one triple integral going from 0 to -2x plus 10 on that second set of limits. Okay, well, then let's not deal with that. Let's do x next because we have a definite left and a definite right. So all we got to do is solve each of these for x. So this one here becomes x equals y minus 4. This one here, we got to do a little bit more work. It's going to be, let's see, if we solve that, we're going to have x equals -1/2 y plus 5. All I'm doing is solving for the other variable, nothing crazy, just finding the inverse. And now we've got our next set of limits. Now it goes left to right in the x direction. This is because I wanted to keep it a single integral. There's nothing wrong with doing it as 2 separate integrals. It just means you're going to have to do the triple integration twice. So completely user choice. So left was y minus 4, and then up to -1/2 x plus 5. Cool. Everybody okay so far? I mean, we're slowly increasing the complexity of these, right? There's a little bit more going on each time. All right, last thing are the y's. Y on bottom is clearly at y equals 0. So that one's easy. To get the other y, we need what that point is, okay? That point is occurring at the intersection of our 2 planes. So basically, you're going to have to set these 2 equations equal to each other. It doesn't matter which ones you do, but we want the y value. So if you just want to solve for y, you could set these 2 equal to each other because they're already ready to give us y. Equals -1/2 y plus 5. But if you wanted to, you could set the other 2 equal, get x, and then plug x into either one of those equations to get y. We just don't happen to need the x with the way we're doing it. So add the half over there. So that's going to give us 3/2 y on this side. Add the 4 equals 9. Multiply both sides by 2/3. That's be a 3. And that's going to give us y equals 6. Again, if we want the x value for that, we can plug this into either equation, y minus 4. So this is the point 2,6. And there is our upper limit on y. Again, I know I keep sounding like a broken record, but those last 2 sets of limits are what you guys have already been doing. You guys have integrated over regions like this for a couple of weeks now. It's basically being able to identify that region. So really our focus is how do we get those first set of limits? And then what does that create in the 2D plane? And that's that shadow region. Questions about this one? All right, let's do a different order on this one. Why not? We got it up. Let's see what we can do without making it horrible. All right. So let's go back to our plot and see if we can identify something that's really clear. Some kind of left and right, something that's really obvious, right? So let's bring this guy back around. And what I would notice if I were to do another set of limits next, I would notice that just like, remember that we decided to do X second instead of Y? We're probably gonna, if we're gonna do a different order, the same thinking goes into it. Like if we flip this on its bottom, look if I try and integrate with respect to Y, the edges are different here than they are here. So we don't want to do Y first if we want to keep this as one triple integral. So we're going to want to do X first. And X is going to go from left to right. So it's going to go from this plane over to this plane. Once again, we got to remember what those equations are. I kind of erased it on the board, but okay, so what plane is this? Well, is it this one? No, that's the one that's on the right. It is this one, y minus x equals 4. So we're just going to solve y minus x equals 4 for x, and that'll become our lower limit because that's the left. Or in this case, the way I have it, the bottom, right? It's going from the negative x to the, actually it is the bottom. That's kind of cool. A nice way to think about it since we can rotate it. Bottom to top, because there's our positive x. So it's going from that plane, y minus x equals 4, except we want to solve it for x. So y minus x equals 4, solve for x, add the x, subtract the 4. Y minus 4 is our lower limit. Our upper is that other plane solved for x, right? This guy here. So subtract the y and the z, divide by 2. So you'll get, let's just write it this way, 4 minus y minus z all over 2. That's our upper limit. We now got rid of the 3D aspect, right? So now x is done, we're in the YZ plane. All right. So you need to think about what this thing looks like in the YZ plane. So let's flip, let's see if we can find an angle that gives us a good shadow region view of what the YZ plane looks like. It's not pretty, but it's going to be this triangle right here. Does that make sense? Because that's going to be what creates the shadow region. So it's going to go down to here to z equals -6. We're not going to have to worry about any negative y values because we're bound by x equals 0. So the big thing we have to figure out is what's happening here, right? So what? And I know it's not a real distinct line on the way this thing is drawn, but that line right there is the intersection of the pink and green planes, right? So here's what this thing kind of looks like. Let's get a kind of a rough sketch so that we can mark on it. So there is our YZ plane. And we got a line coming down like this. And right there, that is z equals -6. All right. Now it's the intersection of these two planes is what's creating that line. And we want it in terms of y and z, right? So here's what we got to do. So we have these two planes. We have 2x plus y plus z equals 4, and we're looking for where it intersects y minus x equals 4. We're looking for the intersection of these two. X equals 4. So what we'll do is we'll solve this guy for X again, which we know is X equals Y minus 4. We'll plug this in to that X. So this will give us that plane in terms of Y and Z. Plus Y plus Z equals 4. Now, something I want to mention as I'm going through this. We didn't have to do this one this way, right? We already had a method that worked. I'm showing you this because it just to get you thinking in these different directions. A lot of them are doable. So what do we have? 2y minus 8 plus y plus z equals 4. So we got 2y and y, that's 3y. So 3y plus z equals 12 is the equation of that line. Well, the way I have it set up, we could do z next. So, and this one could be done in either order based off of our shape. So z equals 12 minus 3y. So we can go from -6 up to 12 minus 3y in the z direction. Minus 3y. So the last thing we have is what we're doing in the y. So y is clearly going to come from 0 out to whatever this point is. Well, remember this is the point this is where z equals -6. So this is something we can solve for y. So we get -6 equals 12 minus 3y. So subtract the 12, so we get -18 equals -3y divided by -3. And we get y equals 6, telling us at this point here is 6 comma -6. And there are our limits on y. We could have done z next because of the shape of this. So if we had wanted to do z, this is with z second. When going this direction, we could have done z next. We would have just solved this for y, right? Gone from 0 to this thing solved for y. And then z would have been -6 up to, we can see that our z intercept here is 0, 12. Now, all of these would have worked. Because of time, normally if we had more time, we just put all these into Symbol Lab and verify this. But I don't want to use up the time for that. But that's something that when you're working on these, you can do. If you're like, oh, I want to try this, I want to take this one and try a different order. Put it into the Symbol Lab or Wolfram and make sure you're getting the same thing. Questions about this one? I know I'm throwing a lot at you at once. Like I said, all this is being recorded, so if you ever want to look at it later, you can. But I want you to just see the flexibility of these things. And the key is to identify those inside limits and then work from there. We're going to do one more. And I'm only going to do one order of integration on this one because there's one to me that is really obvious and the rest of them I don't think are as good. So let's see that. And here is the plot. All right, so just so you can kind of see it, our region is inside this triangle. It's inside the cylinder, but look at what happens in the cylinder, right? It actually is not all the way out to the edges of the cylinder. So start to think about what you might want to do first while I give us some space. This stuff is new for you guys, but eventually you will get to the point where you look at something like this, like, oh, I know where I want to start. So let's look at this region. And you might even know where to start just based off of our equations here. But if I look down the YZ plane, notice how that plane makes a bottom of our region. That plane makes a top. But if I look left to right, well, the left is different here than it is here. So that's telling me that would need to be split into two integrals if I do left to right first versus bottom to top. So I'm already liking bottom to top, but let's take a look straight down. Here's where it really gets interesting. Okay, well, it's circular there and it's circular there. So we could do those, but we would still have to go from this plane to this plane. So the circular region, it turns out it's going to be easier to save to do it a little bit later. I'll show you what that looks like here in a sec. So this thing is set up to do Z first. I think I think Z is the easiest to do first. Let's get this down to a 2D situation and then deal with that, which is much easier because then it's easy to plot. So we have one plane with a negative slope. We have one plane with a positive slope. So we already know our inside limits. So the negative slope, so the lower limit is going to be -3 minus 2y up to 3 plus y. Boom. We are down to a 2D problem. This thing just got a lot easier. Right? Does it make sense how we got those? Okay, so now we got to figure out the next set of limits. This is that shadow region. Notice what's happening. We do have a circle, but we have these lines going down it. So let's talk about what that's going to look like. And let's kind of get, it's upside down. I want to kind of get an XY. Let's see if we can do it from the side. Yeah, doesn't look quite as good. Actually, that'll still work. Let me change the color on. There we go. Now you can see the lines a little better. We have a circle, but there are straight lines going down it. So it's this purplish region in between these two lines here. Okay. All right, let's actually, let me see. Can I? There we go. There it is as an XY. This will make it a little bit easier for us to think to conceptualize. So what's happening? Clearly we have a circle, right? That's coming from the x squared plus y squared equals 16. So we have a circle right here, but it's being cut off in two places. We see it's being cut off here, and we see it's being cut off a little bit more in right there. Okay. So we need to think about order. And this is going to make things either easier or harder. There's a definite left and a right. So this is the X, this is the Y. If we try to do top to bottom, we would have to break this thing up in so many places. This would be 1, 2, 3, 4, well, not 4, 4, 5. What has to be broken up into 4 or 5 integrals if we try and do top and bottom next? We have a very clear left and a right. It is coming from the cylinder. All we got to do is solve that cylinder for X, and we've got our next set of limits. So we're going to go negative square root of 16 minus y squared to square root of 16 minus y squared. And we're doing X next. Everybody okay with that? That's taking us from here to here. Now this thing here was created by the plane y equals 3. So we actually even already know the upper limit. All we need is that bottom limit. Well, where is that bottom line coming from? What's creating that bottom line there? This line right here, what's creating that? And if we turn it back to its side, I bet you can see it. That's what's right there, is what's creating that line, right? It's the intersection of those two planes. The 3 plus y, and then, so it's the intersection of these two planes. Set those equal to each other and find where they intersect. So 3 plus y equals -3 minus 2y. So add the 2y, we get 3y, subtract the 3, we get -6. And there is our lower limit. And, like I said, I'm not going to do any other orders on this one because it gets really difficult to do in any of the other orders on this one. So this is one where we really want to be intentional. We find that top and the bottom. And think of that as your goal as you're getting used to triple integrals. Identify a very clear top and bottom, because after that, it just becomes a 2D problem. Questions about this one? Okay. Oh, just a couple notes before we try some problems. Like I said, basically what you're doing is you're integrating over the volume of a solid region. And if you have some function, one way of conceptualizing what this does is to think of that function as being the density, and then you're calculating total mass. So this can be used for center of mass, those kind of things. And last thing, when setting up a triple integral, the outside limits must be constants, just like on a double integral. The middle integrals can involve only one variable. You have to have a chance to integrate it out. And the inside can depend on two variables. Doesn't have to, but it can. All right. Now, I want to give you guys a chance. If you're good on questions, then let's try a few. Now, I've already set up some of the ones from the worksheet. So I already did. Which ones did I do? I did 2, 4, and 6. So I did all the evens. So ones that be good ones to try are maybe like number 1 and number 5 would be really good ones to really try to get this idea of setting these up. So let's work on 1 and 5 and see how we feel about those. Same thing for you guys at home. I'd say 1 and 5 are good ones to work on for setup. And then if you have time, if you want to try calculating either one of those or one of the ones from number 7, that'd be fine too. Or even one of the ones we did on the board, since we didn't actually calculate them. But like I said before, set them up, put them in Wolfram, see how you did. All right.